All right. Welcome back. Welcome back. Today we'll continue our journey into dynamic programming. All right. So let's start. Okay. So what happened last time? So last time we looked at the longest path in a DAG problem, and we designed an algorithm for it. I went over it very slowly because it's sort of our first example of dynamic programming. And we saw that there's a recipe to do it, and the recipe was to design the algorithm. We define some subproblems, which are smaller instances of the problem, and we write a recurrence among these subproblems, and finally, we use the recurrence relation to solve the subproblems in a particular order, and we wrote code for that. So that's what we did last time. We did it for this problem of longest in path in a DAG. Okay, so what we'll do now is we'll actually look at an example or a couple more examples of problems for which we'll design algorithms using this method of dynamic programming. Okay? Okay, let's start by looking at the first one on this set. So it's called the knapsack problem. So what is a knapsack problem? So the story is kind of strange, and story is kind of strange, but the problem pops up everywhere in different forms. But I'm going to stick to the story, the original story. The original story is you're robbing a museum or something. You're robbing some place, and then you have a knapsack. And you have a knapsack, and in the museum there are objects, items, different items. So there's item A, B, C, D, E, F. These are different items, each of which has a different weight, and each item has a different value. So item A weighs, let's say, 15 pounds, and its value is $43. It's like a really cheap museum there. And so you have a bunch of these items, and you can only carry some maximum amount of weight. There's some upper bound on how much weight you can carry. What you want to carry is the most valuable bundle of items. So you want to figure out what is the most valuable set of items that you need to put in your knapsack. So here's the input. So the input is a set of items with weights and values. Okay, so you have a set of numbers, W1, V1, W2, V2, and then Wn, Vn. Okay? You get weights and values for n items, and you also get a total budget or total maximum weight. Or let me use the word total weight, maximum possible total weight, or that you can carry. This is some number, capital W. So your input consists of these numbers, and your goal is to find a subset of items with total weight less than capital W and maximum value. So you want to maximize the total value, but your weight has to be less than capital W. Okay? So now, as you can see, this is a very, very ubiquitous problem. Like, in any time you have some budget, let's say you have some budget, and let's say for an ad campaign, and you have a bunch of different kinds of ads that you can run, let's say television ad and newspaper ads or whatever it is, and then each kind of ad gives you reaches some number of people. Okay, so your weight is the amount it costs to run an ad, and your value is the number of people you reach. And so if you have a budget and you want to reach the maximum number of people within that budget, that's what this knapsack problem is, right? So you can see that in any kind of budgeted problem where you have a budget and you want to maximize some value given that budget, and this budget could be, money or processor speed or whatever it is, this kind of problem shows up. So it's a really ubiquitous problem. It's going to show up everywhere. And you can see that it's fairly complicated. So you could, for example, in this example, let's say the total weight is 30. Okay, total weight is 30. Then you could pick item A. Okay, this costs you weight 15. All right. Okay, now after we picked item A, now there's this question: do we still have item A to pick again or not? Okay, and that's sort of problem definition. So let's start with a simple case where you allow repetition. So knapsack with repetition is when you can pick the same item multiple times. So in this case, if you can carry 30 pounds, you can pick A, which has weight 15, another copy of A, which is weight 15, and then you get 43 plus 43. So the total value of this bundle is 86. Okay. Alternately, you could pick A, C, and D. Right, that is 15 plus 7 plus 8. It's also less than 30. Okay, and what is the total value you derive? It's 43 plus 19 plus 23. That's 84. So all sorts of combinations, and you want to find the particular subset of items or particular combination of knapsack of items, bundle of items that maximize the value. Okay? Is the problem clear? So that's the, yes. The question is, if item I is heavier, is it always more valuable? No. Yeah. Yeah, in this example, I guess it happened to be that way, that heavier items were more valuable. But in general, you just have weights and values. Thanks. Any other question? Is there a natural, what sort of greedy strategy would you use here? Yeah. Always pick the most valuable one. Yes. Yeah. Yeah. So there's another one which is most value per weight. So most valuable one seems bad because imagine imagine my W was, suppose I pick the most valuable one every time. Let's say our W was 21 or something. 21. Okay, then you would end up picking the first item because it's the most valuable one, but you're better off picking 3 copies of C because it makes sense that somehow picking the most valuable one, you might have leftover space in your knapsack, which you might not be able to fill with anything else. So that's a bad move. Picking the one which maximizes the ratio of value per weight, that actually makes a lot of sense because if you really, if these items were really divisible, like, imagine these were some sort of liquids and you can take fractional amounts of these, then imagine you just had, a glass and you had liquids and you can take any fractional amount of any of them, then it clearly makes sense that you should just fill up your cup with the one which has most value per weight. Right? If you had gold and silver and platinum, you'd just pick up platinum because it's most value per weight. If you could pick fractional amounts. So if you could pick fractional amounts, this problem is kind of easy because you just pick the one which has most value per weight, clearly. But then here you have these integers. You can't really pick half of A, or you have to pick the entirety of A or not. So what happens when you have this sort of integer constraints is that you'll have this issue of leftover space in your knapsack. Right? Maybe the most value per weight is object A, and you pick that, but then there's some space in your knapsack which you're wasting because maybe nothing else fits in the space that you have left over. And that's the issue. So the thing that we are sort of fighting against here is that for every object, I have to either pick the entire object or not. And so there's this tension between sort of having some leftover space in my knapsack because I can't fit in anything versus picking the most valuable value per weight every time. So that's the issue. So it's a kind of you can see that it's greedy strat. For pretty much every greedy strategy that you come up with, there's going to be a counterexample where it doesn't work. Okay? And we'll design an algorithm for this problem. But actually, this particular example that I've picked up, this particular problem, with especially in knapsack with repetition, it turns out to be a problem that we already solved last class. Okay, I won't design an algorithm for this right now because this problem, you can see, is equivalent to or can be written as longest path in a DAG. Okay, it's a good exercise to try to come up with a DAG, directed acyclic graph, in which this is the longest path problem in there. Okay, and but I'll skip ahead to the more interesting version of this problem, where it's the same problem, but no repetition. The key point is no repetition. So I just wrote down the same problem. It's exactly the same problem. You have a set of items with weights and values. You have maximum total weight. You want to pick the bundle with the maximum weight, maximum value. But each item, there's just one copy of each item. You can't pick 2 copies of A or 3 copies of C, and so on. Okay? This is a more interesting variant of the problem. Okay? All right. What is the naive algorithm for this problem is to just try every possible subset of bundle items. There are 2 to the n different subsets of items that you could put in. If there are n items or 2 to the n different subsets, the naive algorithm would be to try every possible one, so that's roughly 2 to the n time. It's exponential time. Okay, I just sort of, that's good to keep in mind. What's the naive algorithm? What are we fighting against? Okay? All right, so we'll design an algorithm for this problem now. We'll use the recipe of dynamic programming. Okay, so what does the recipe tell us? The first thing it says is define subproblems. Okay, what are subproblems? I never defined them. I didn't define subproblems. So what are subproblems? So it's sort of smaller versions of the problem that you use in your algorithm, but I don't want to formally define it, but I want to tell you how one could come up with subproblems. So here's sort of so before I start defining subproblems, the way I'm presenting this algorithm design is I'm going to follow the recipe for dynamic programming as is, to the dot. I'm going to first define subproblems, then I'm going to write down a recurrence relation, and then I'm going to write down the algorithm. Okay? And usually it's not a good idea to tell people how to think, but this is a beneficial thing. So just stick with me. Let's not try to come up with an algorithm out of scratch. Let's follow the recipe for how to come up with the dynamic programming for knapsack, and then you'll see the benefits of the recipe. Okay? So here's a recipe. So I want to come up with smaller instances of the problem, and so how do I come up with the right ones? This is what I would do. It's not the only way. What I would do is I would try to imagine the optimal solution. Okay? Imagine the optimal solution and break it up into smaller pieces. Okay, this is it's a little bit different than our many other algorithms. Like greedy algorithms try to build the solutions from bottom up. You keep adding edges, and each time you try to make sure you add edges based on some policy. Here, it's kind of good to think of the algorithm or algorithm design as top-down. So first, just try to imagine an optimal solution. Okay, so what is optimal solution here? You know, there's this, I don't know, I mean, depending on how vivid your imagination is, there's some knapsack and then there's some items here, right? You imagine the optimal solution, it has some things here. Okay, and then you want to try to break it up into smaller pieces. All right, so, okay, what does breaking up into smaller pieces mean? You know, let's ask let's just take out an item from here. Okay, you know, this is the optimal knapsack solution. So it has some items and it has some weights and values. If I break it up, if I take out an element from here, okay? So if I take out A, let's say, suppose A is part of it. Right, I'm assuming that, suppose A is part of the solution, I take it out. Okay, so if I took out A, then usually when you break up an optimal solution to a problem, you end up with optimal solutions to smaller things. For example, if you take a shortest path and you cut it anywhere, the two pieces are also shortest paths, right? So that's the important here. So what's going to happen is if you take the knapsack problem and if I take out an item A from the optimal solution, okay, what is going to be true about this thing? What's left? Well, it's going to be the optimal way of filling up the rest of the weight, right? There was some total weight, capital W allowed. This knapsack had total weight, capital W, okay? And if item A was part of it, then once you take out item A, whatever is left, that knapsack, is the best way to fill up the rest of the weight, clearly, because if there's a better way, you would use that. So whatever is left is the best way to fill up the rest of the weight, meaning the subproblem, like at first it seems like, so the knapsack, if the optimal knapsack minus the item A, right, this looks like the optimal knapsack for weight W minus W weight of A. Right. Does that make sense? If I take the optimal knapsack and take out, assume A is part of it. If I took it out, then what's left is optimal knapsack of weight W minus WA. Okay? So this seems like you would want to define a subproblem to be, tell me the optimal knapsack for every possible weight. Right? So the trial one would be to say, let K of little w be the optimal knapsack for weight little w, okay? And you can try to define this for each weight w equal to 1 through capital W, okay? This seems like a reasonable subproblem. And you can try to write a recurrence relation with this. Okay. Is there a question here? Yes.
Can you assume anything about the A that you're removing? So is it the least valuable or the most valuable item? Or just the type item?
Yes. The question was, what am I assuming about the element that I removed? I'm not assuming anything. I really don't know which item is part of the knapsack. So right now I'm sort of even just trying to see if there was a knapsack and if there was some item there, if I took it out, how does this rest of the thing look like? Can I say the rest of the thing is a solution to some smaller problem? And what we see is that the rest of the thing seems like a solution to the following smaller problem. You have weight, which is W minus WA, whatever the weight of A was, whatever you took out, and you want to fill it up optimally. Okay? Yes. Oh, yes. Yeah.
But if you say is the optimal mass factor weight W minus WA, then you're not explicitly saying A, right?
Yes. Right. So that's a good point. We'll come to that. Yes. That was my next point. Was there
We are considering every weight from 1 to W. Isn't that kind of wasteful since not every weight is
yes. So okay. So the question was, this seems wasteful because maybe not every weight is possible. For now, we'll just try to come up with some algorithm, and then we can try to optimize it, improve it better. Now I'm just actually sort of dissecting how to come up with the subproblem. So, okay, this sounds fine, except if you recall, we said the knapsack should have no repetition, meaning no element should appear twice. So, what's left? This is so this is not correct. It's not the case that in what's left is the optimal way of filling up W minus WA. It's actually the optimal way of filling up W minus WA when you don't have A available to you. Right. If you take the optimal knapsack and remove A, then what's left here is the optimal way of filling up W minus WA without using A. Does that make sense? It's because we're not allowed to use the same element twice, what's left is actually a solution to the following strange problem, where you are a different kind of problem, which is optimal way of picking up W minus WA without using A. Okay? So you went from trying to find the best possible knapsack without repetition to, so let me write, to finding the best possible knapsack for weight W minus WA without using A. Right? So let me write down what optimal knapsack was. It's optimal knapsack for W. You started with optimal knapsack for weight W with all the elements available to you. And now, after removing A, you're left with this. The subproblem looks different. Somehow there are these precluded elements, right? Earlier, all elements were available to you. Now, something is precluded. Okay? And it seems to suggest that our choice of subproblem is more complicated than what I wrote here. Right? This attempt one that we did, this trial one, K of W is just the optimal knapsack for each weight without telling me which elements are not allowed or which elements are allowed. Right? So maybe the next thing to try would be, you'd say, oh, let's ask for the following more general thing. So this is attempt 2. K of W, comma, let's say some set F. This is a weight, target weight, and this is a set of forbidden elements. Okay? I have a target weight and I have a set of forbidden elements, and you could say K of W, comma, F is the optimal knapsack with total weight less than W and using no forbidden elements. So, I'm sort of dissecting how you come up with the answer. So it does look, a little bit crummy and inelegant, but this is how you would come up with the answer. You'd say, okay, I'll try this first, and this doesn't work. So I need to add more subproblems into it. So you could say, oh, let me just add, every kind of subproblem that I could see. Every kind of subproblem that I can see is I'm left with some weight, and I'm left with some set of forbidden elements that I can't use. And then this should really be everything, right? In fact, you can write a recurrence relation with this. Because now with this you can say, if I take out one more element, then that becomes forbidden and my weight decreases. So this seems like a full set of subproblems. What's the issue with this? What's the issue with this? Yeah.
We don't know about which element we should not
Right. Right. Yeah. So. Yes.
This object seems really big or short because there's lots of possible sets of forbidden elements.
Yes. Right. So the thing is, the number of different. This is a fairly valid set of subproblems. There are too many different subproblems here, right? How many different weights are possible? Of course, we already saw it could take 1 to capital W. And how many different set of forbidden elements are there? Well, we don't know. It could be 2 to the n, right? Like all possible subsets, right? So there's way too many subproblems, okay? And the issue is somehow the set of forbidden elements seems completely arbitrary subset, okay? So then you would try to find some way in which you can control the number of subproblems here. The number of subproblems here just blow up too many, right? This just became too many. So how would you control it? Well, in some sense, it's a very small trick in this case, and it's a useful trick, but it's a very small trick. Is that when I wrote down this equation, optimal knapsack for W minus A, right, is optimal knapsack for W minus WA without using A. This element A, I just picked out arbitrarily from the knapsack. I just said, okay, take some element from that's in the knapsack, take it out. Okay? But what if we did this in some order? What if we decided, like in some order? Let's just say, ask, is element N part of the nth element, is it part of the knapsack or not? Okay? So the thing is, if you did it in order, the set of forbidden elements will always be a nice family of subsets. Okay? So now I'll show you the actual, recurrence here, actual set of subproblems and the recurrence. Okay? So here's if I was trying to dissect how to come up with the subproblems. If you didn't follow this discussion so far, if you're uncomfortable with it, just forget about it. Let's come back to, I'm going to show you the actual answer, and hopefully that will eliminate what's going on. Okay? So here's an actual answer of how the subproblems work here. Okay? Again, so I'm going to imagine the knapsack, okay, and I'm going to ask the question, is element N part of it? Okay, is element N, is the last element, right, is the item N, sorry, I should say item N is the item, the nth item, WNVN, is it part of it? Okay? there are only two possibilities. It's either part of it or not part of it, right? So if it's not part of it, you're only allowed elements from 1 through n minus 1. If it is part of it, again, you put it in there, and you're still only allowed elements from 1 through n minus 1, right? So the set of elements that I'm allowed is some subset of 1 through I. So my subproblem is k of w comma I. This is my subproblem, is the optimal knapsack with weight less than W, with total weight less than W, that uses only elements from 1 through I. Okay, I'm going to read it again. This is, usually the definition of the subproblem is the most important part of DP algorithm. So I'm going to read it again. K of Wi is the optimal knapsack whose total weight is W, and it only uses elements from 1 through I. Okay? It's a subproblem because if I want the answer to my original problem was K of capital W, comma, N. This is the answer for my original problem, right? These are goal, right? This is our answer. Because it's the optimal knapsack with total weight capital W that only uses elements from 1 through N. Okay? Okay, so this is the key definition. Once you come up with the right definition for a DP subproblem, the rest of the algorithm will sort of write itself. There's only one. Most of the time, you don't need any more new ideas. Okay. Sound fine? Okay. All right. So, okay. Now that we have the subproblem, the next thing is to write down the recurrence relation. Okay. I'm going to copy back the thing. This is our definition. Okay? So now I'm going to write the recurrence relation. So how do I write the recurrence relation? Well, it's going to be as follows. Okay, let's look at the optimal knapsack that uses elements from 1 through I with total weight at most W. Okay? If I look at that knapsack, there are two cases. Right? Either it contains element I or does not contain I. There are two possibilities. Right? Either it contains I or does not contain I. If it contains I, okay, or let's say it does not contain. If it does not contain I, then somehow what's in the knapsack is an optimal knapsack for weight W, which uses elements 1 through I, but not I. So it uses elements 1 through I minus 1. So in this case, it's just K of W comma I minus 1. On the other hand, if it does contain I can take out the element I. So I get a value of V sub I. And in what's left, I have weight which is W minus Wi and elements from 1 through I minus 1. And so that's my recurrence relation. It either contains I or does not contain I. In either case, the solution is given by these two possibilities. And so the actual answer is the maximum of these two possibilities. Okay? Any questions so far? one point of confusion which students have at this point is that, I think one point of difficulty in understanding is that up to this point, I'm not trying to design an algorithm. I'm just trying to write a recurrence relation. As I said in the beginning, let's follow the recipe. I'm not trying to design this is not an algorithm, and so it seems to assume things. It seems to say, oh, if it contains I, it's that. If it does not contain I, it's this, and it's the max of these two possibilities. But we're just writing the recurrence relation right now. Okay? There was a question here? Okay. Okay, so that's it. So you have a recurrence relation. And so now we have our subproblems and we have a recurrence relation. Now we can basically write down the algorithm. All right? So what is the algorithm? So in order to write down the algorithm, I'm just going to illustrate what the subproblems are. So we have all of these subproblems, which are, this is k of 0, 0, sorry, k of 0, 1, k of w, 1, and then you have k of w, n. So all of these numbers, k of w, I. Okay. There are how many subproblems? There are n times capital W subproblems. Each of them is defined by just this. It's the optimal knapsack for total weight at most W with elements using 1 through I. Okay? And what we have is a recurrence relation. We have a recurrence relation where we have expressed k of Wi in terms of, so we've expressed k of Wi in terms of something k of W minus Wi, k of W, I minus 1, which is this, k of W, I minus 1, and then k of W minus Wi, I minus 1, which is somewhere on the, k of Wi, I depends on k of W, I minus 1, and then something with k of W minus Wi, I minus 1. Okay? So that's what the recurrence relation says. Right? There are n times W subproblems with these dependencies. In order to know the value of k of Wi, I need to know the value of k of W, I minus 1 and k of W minus Wi, I minus 1. Alternately, if I know the values on the right, I can immediately calculate the value on the left, right? And so that's the dependencies on these subproblems. Each of these subproblems depends on some other ones. In order to know the value of this, I need to know the value of some things before it, okay? And base cases, I do know the value of everything on the first column. If I have 0 weight, I cannot carry anything. The value is 0. So all of the subproblems on the right, we know the values. These are all 0. Because if the weight is 0, then the value is 0. Okay? And so now we can just compute the value of this subproblems in an order, in some order. So, we know that every subproblem depends on something in the previous row. Okay? In fact, this is a DAG of subproblems here. Right? This is a DAG of subproblems, meaning the dependencies don't form a cycle. Okay? In general, if you write down a recurrence relation, it's not clear that they don't form a cycle. But here, the dependencies don't form a cycle. And an easy way to see that is because k of Wi only depends on k of something, I minus 1. So you can see that all the arrows in this DAG go upwards. Okay? So I just need to calculate the values of all these subproblems in some order. You can pick basically any topological sort of this DAG to compute the values in. But let's just follow the most naive order, or simplest order. I'm just going to calculate the values in the first row, then the second row, then the third row, and so on, until I reach K of W, n. Okay? I'm going to calculate values in this order. So now we can just write the code for the problem. So it's going to be so let me just initialize K of 0, I to be 0 for all I equal to 1 through n. Okay, I know that. And then for I equal to 1 through n, for weight W equal to 1 through capital W. Okay, what do? You just write down the recurrence relation. K of W, I is the maximum of two possibilities. Okay, either it contains the ith element, or either it doesn't contain the ith element, in which case it is K of W, I minus 1. If it contains the ith element, it has to be K of W minus Wi, I minus 1 plus Vi. I'm just writing down the recurrence that's here. Okay. And then you return the top left corner, which is K of capital W, n. That's your answer. And so that's basically the code. To be correct, one should you add some check here so that the indices don't go to negative. You should only do it if Wi is smaller than W. Okay, yeah. Okay, so that's basically the code for this problem. Any questions on this? Yes.
When you make the call to K of W, I minus 1, if your W is non-zero, won't that give you some uninitialized value?
Right, so you're saying K of, okay, I guess the question was about, what about K of W, 0? I think we should set those also to 0. K of W, 0 equal to 0 for all W equal to 1 through capital W. Okay? If you can't pick any element, also you should be, if there are no elements available, then your value should be 0. So just base cases of the recursion. Any other questions? Yes. Yeah. So it's a nice question. The question was, does it matter if we flip the for loops? Like, does the order of these for loops matter? What do people think? Does the order of the for loops matter here? Yes? Yes? Actually, I think it's no, because if you look at the DAG, all the edges are going upward and towards the right. So if you actually calculated these, and you can actually calculate these subproblems in a different order and you'll be fine, which is you can go this way and you're still fine. In fact, there are many ways in which you can traverse this DAG, all of which are fine to calculate the order. You can, in fact, take I think you can even do, if you're crazy and you just don't like readability at all, you could follow a snake route. And it will be a perfectly legit piece of code that works, right? It's sort of, yeah. And that would still give you the right answer. So there are many ways in which you can order the vertices in the DAG and solve the problems. The only thing you need to ensure is whenever you're trying to solve a particular subproblem, all the things that you need have already been computed. Okay? And there are probably many ways to do that. Yes?
Is it reasonable to expect that whenever we're doing dynamic programming, we will eventually reduce the problem to a DAG and then trace all the way back to the origin?
So the question was, whenever we are doing dynamic programming, is it reasonable to expect that the recurrence relation will give us a DAG? That's something we need to ensure when we are writing down the subproblems. You could write down subproblems for subproblems where you have a cycle. It's possible, but quite often that doesn't happen because intuitively you have a notion of size in your mind, like the number of items or the weight or something. And intuitively you're reducing that parameter when you write the recurrence relation. But you can write recurrence relations where nothing decreases. For instance, here's something, right? For look at shortest paths problem. I could say the distance from I to j is the minimum over all k of the distance from I to k plus distance from k to j. Okay? The triangle inequality. So for shortest path problem, look at the following recursive relation. Comma j is minimum over all vertices k of distance from I to k plus distance from k to j, where d is the shortest path, shortest paths problem, or the length of the shortest path. Okay, minimum over all vertices k. This is a legit recurrence relation. It's true. As a theorem, it's true. If you look at any graph, look at the distances in the graph or the shortest path lengths in the graph. Distance from I to j is at most the minimum over all k. It's in fact equal to the minimum over all k of distance from I to k plus distance from k to j. Right? This is a true fact, but it's not good for dynamic programming because if you write down the subproblems here, there will be no DAG. Every distance depends on every other distance. And there's no order in which you can calculate this a priori. Okay, so it is possible that you can end up with cycles in your subproblems, but quite often, if you have some intuitive notion of size or something that's going down, and from left to right, size or the number of items or something, then you'll never have this issue. Okay? Any other questions on this? Okay? Yeah. Without repeated items. Oh, the question was how to construct DAG for the one without repeated items. I will not. Some of it is in the books. I would let you, if you have that resource, if you want to look it up. I will not answer that question right away. I'll give you. So something to think about is, let's say you had a knapsack where you had weights and heights, two different things. So you wanted the total weight of everything that you carry to be at most W, and the total height of everything that you carry to be at most H. Okay? So you have weight and height. And you want the total weight and the total height to be bounded by W and H, and find the maximum possible value you can get. So try to come up with subproblems for that, just for practice. All right, so we'll look at more examples of DP next class.